Okay. So welcome back to the lecture series on electromagnetic waves. So we know that in the previous class we were discussing about the wave propagation in a lossy medium, good conductor, and I think first we have discussed the wave propagation in a lossy medium, good dielectric, and also we discussed in the good conductor. Okay. So in good conductor, okay, so these are the wave characteristic parameters like alpha, and we obtain that is alpha is equal to beta. Okay. So alpha is alpha decides the attenuation factor. Okay, and we know that in this particular case, in the good conductor, alpha is equal to beta, which is given by root of pi f mu sigma. Okay. And the intrinsic impedance of the medium is given by this. We have also an equivalent expression given by this one. We find in a good conductor that is alpha is equal to beta, the phase constant is equal to that alpha. Okay. And next, v, okay, that is the velocity or the phase velocity of wave propagation is still given by the same expression omega by beta, but I should remind you that the beta will not remain the same for all the wave propagation in the different medium. In different medium, you have the different beta. Okay, well, the wavelength is given by the same expression 2 pi by beta. Okay, so next, from this characteristic parameter, we can write the expression for the electric field. Okay, and by writing this expression for an electric field, okay, I have referred for this general medium because we know what is the electric field. Okay, we know what is an electric field in a general medium. Okay, which is given by Ex naught e to the power minus alpha z cos of omega t minus beta z ax. The only thing is, okay, these parameters will change with respect to their expressions. Okay, for a general medium, we have alpha given by some quite big expression. I hope you remember we have derived this, and even the beta we have some kind of a big expression. Okay, but as I try to apply the same thing for a good conductor and good dielectric, okay, they reduces and approximate to the simplified expression as shown here. Okay, so in that sense they will change. Okay, so next, similarly, we can write the expression for a magnetic field. Okay, and we know that the amplitude of magnetic field related by the intrinsic impedance of the medium. So it is Ex naught by eta, and as the eta is really a complex, okay, as the eta is really a complex, so which has magnitude and a phase, and the phase is taken care over here. Okay, it's actually this is a magnitude, and you have e to the power j45. When I take it to the numerator, it will be e to the power minus j45, and that is being observed here. Okay, and from this expression, we could really make out that E leads the edge by 45 degree. Okay, so this is what we have seen in the previous class. Okay, so now I would like to discuss the one more concept called as skin depth. As the skin depth. Okay, so the skin depth we would like to define as. Okay. So we know that the E and H wave travels. Okay, as E and H wave travels in conducting medium. In conducting medium. Its amplitude is attenuated by a factor called by a factor e to the power minus alpha z. Okay. So now let us say that the distance delta, okay, through which wave amplitude, okay, say that the wave has traveled a distance delta, okay, and by doing so, say that it has the distance delta through which wave amplitude decreases, wave amplitude decreases to a factor e to the power minus 1 of original value that is 30% of the original value. In that case, I would say 30% of original value. Okay. So what I want to mean is, okay. So we know that these waves, as they propagate through medium, this conducting medium, its amplitude attenuates. It's an exponentially decaying sinusoidal variation. So this is as a function of the z, and this is my e, and my the peak value is ex naught. My peak value is ex naught. Okay, so that it is operating at z equal to 0. Okay. Now what is happening as I travel through a distance, okay, along the z, okay, the amplitudes keep on following exponential. Okay. Now what I say that, okay, if I travel a distance delta, okay, some distance delta, okay, through which the wave amplitude decreases to a factor of e to the power minus 1 of the original value. Okay. So I know that initially the amplitude Ex naught, its amplitude is, given by Ex naught e to the power minus alpha z. Okay. This particular exponential decay, okay, of an amplitude is given by this one. Okay. Now next I say that Ex naught e to the power minus delta, alpha delta. If I take a distance z equal to delta, okay. Now what happens to an amplitude? It falls by a factor of e to the power minus 1. That is what the statement tells us. Okay. Decreases to a factor e to the power minus 1 of the original value. What was an original value? Original value was this, z was equal to 0. And I traveled a distance of delta. Okay. And if I say that the amplitude has fallen by a factor of e to the power minus 1. Okay. So you could see that from this expression, I could write minus alpha delta equal to minus 1. Okay. And the delta is equal to 1 by alpha. Okay. 1 by alpha. Okay. Now what does it mean that? Okay. So what is that distance? Okay, when you travel, okay, which makes the amplitude to fall, okay, to decrease by a factor of e to the power minus 1 of original value, or 37% of original value. To fall at 37% of an original value. That distance is given as delta. Okay, and its expression is given by delta equal to 1 by alpha. Okay, delta equal to 1 by. That is the skin depth. Okay. So in very simple, in very simple way, what I mean is, Okay. If the wave propagates, I would like to show by distance of delta, by distance of a delta, its amplitude, if you try to check now, its amplitude will fall okay. How much? It will fall by a factor of e to the power minus 1 of the original value. Of the original value. That is what it means to be. Okay. If you travel a distance of delta, its amplitude will fall, okay, fall by a factor e to the power minus 1 of its original value. Okay. And that is called as the skin depth of that conducting medium. Okay. E to the power minus 1 is means like 37% of the original value. Okay. So this is the skin depth. Okay. And we have an expression, okay, for a skin depth. That is from that definition, we obtain an expression for a skin depth, which tells that delta is equal to 1 by alpha. And you could see that we know what is alpha, which we have derived in the previous expression, in the previous session, which is given by a root of pi f mu sigma. That is meters, which is measured in the meters. Okay. Now you could really check that this particular delta is a function of frequency. So it's very obvious that as you increase your frequency, okay, or you could say that as you increase the conductivity of an medium, this skin depth keep on reducing. So what does it mean like? So initially say that you travel this much of distance, okay, and you check that amplitude has fall by 37%. If I really increase frequency, it is really possible that if I really travel of this much of distance, okay, you may really find that, okay, the amplitude would have fallen by 37%. You again keep on increasing frequency, okay, you may really find that, okay, you travel a very short distance and you will find that the amplitude has fallen by 37%. It's really dependent upon that frequency. Okay. So what we say that the skin depth is measure of skin depth is a measure of the depth to which an EM wave and EM wave can penetrate to the medium. So this is a definition of a skin depth. That skin depth is a measure of the depth to which an EM wave can penetrate through the medium. Okay. Now what happens if you really go beyond this delta, say 2 delta, 3 delta, or 4 delta? You could see that, okay, approximately for a 5 delta, the amplitude will vanish to the 0. Okay. It really depends upon the frequency. We could say that somewhere around for 2 or 3 delta, okay, this particular amplitude almost falls to a 0. That's the skin depth, which measures the depth to which an EM wave clearly can penetrate through the medium. Okay. So we would like to study this with an example. Okay. With an example. Okay. Let us study what is the skin depth. The skin depth in a copper. Copper is really very good conductor with a sigma equal to 5 point, okay, 5.8 into 10 raised to 7 Siemens per meter. That's the conductivity. If you really apply this whole formula, okay, that is pi, mu, and sigma, I can write this delta as 66.1 divided by root f, and it is in the millimeters. Let me form a table which is with respect to frequency hertz, and you have delta which is measured in the millimeters. Say for frequency of a ton, the depth of penetration is 2.8. Okay. At a 60, you check that the depth of penetration is 8.6. At a frequency of 100, the penetration is 6.6 millimeters. And it's 500, 2.9 millimeters. And in terms of 1 kilohertz, it's 0.66 millimeters. And I think 100 megahertz, that is 6.6, you know, yeah, 6.6 milli itself, and then to the power 10, it is 6.6 into 10 raised to minus 4. So can you check how does it is varying? Okay. Yeah. So what I want to tell is, okay, the depth of penetration, okay, the depth of penetration for a good conductor like copper, for a different frequency, at 10 hertz, at a very low frequency, the depth of penetration is 20.8 millimeters. Okay, it means that all this current and fields are confined in that particular depth itself. Because if you go beyond this delta, okay, you will find all the electromagnetic have almost gone to the zero. So if you really increase frequency, you will see that the depth of penetration reduces. It's an 8.6 millimeters. 100 hertz 6.6, 500 hertz 2.9. If I make it as a 10 kilohertz, it is 0.66 millimeters. And for 100 megahertz, it is 6.6 milli into that milli, which is like a micro. It's the distance of a micro, very small. Okay. So this whole thing, we would like to tell that if you really have a conductor, if you have a conductor of a radius A, okay, this is actually having, okay, it is like a solid conductor, okay, which I would like to show something like this. It's a solid conductor of some radius A like this, okay. But when the electromagnetic wave comes from, say, from a free space, and when it tries to enter this conducting medium, it will not really propagate all throughout this whole conductor. Okay, what we really find that all this electromagnetic wave can travel, okay, only to a depth of delta. It can travel only to a depth of delta, and that delta will depends upon that frequency. So you could see that all this current and electromagnetic waves are confined within this small region. Within this small region, its actual radius is A, but it is confined only. Okay, if I will try to take this, it's confined only on a thin layer of that conductor. Okay. Yeah. So we could really observe from the table that as frequency increases, the depth of penetration decreases. Okay. So this phenomena where you observe that the field, okay, decreases rapidly. Okay. So the phenomena where field intensity okay, in conductor rapidly okay, rapidly decreases is known as skin effect. Is known as skin effect. Is known as the skin effect. So what does it mean that, okay, the currents and the EM fields are all confined on the thin layer or a skin of the conductor, but not the in the whole, but not in the whole radius of the conductor. Okay, yeah. So this is all about the skin effect. Okay. And one more thing is that this particular, okay, delta equal to 1 by alpha, which is the skin depth, is really applicable. Okay, this formula is really applicable, okay, for conducting medium also. Because even in the lossy medium or a conducting medium, we observe that there is a, we observe that, there is an attenuation of an amplitude of both electric and magnetic field. There, even we can really apply. Okay. But for a good conductor, the formula is given by 1 by root of pi f mu sigma. That's the difference. Okay. Okay. So with this understanding of a skin depth, okay. Now I would like to write my wave characteristic, which we have already written, okay, for a good conductor. I would like to write the whole wave characteristic, okay, in terms of this skin depth. So let's do that. We know that for a good conductor, the alpha is equal to beta. Okay, alpha is equal to beta. But I also know that the alpha and beta. Just now we have checked that the alpha is equal to 1 by delta, which is skin depth, Okay. So which means that I can write this as, we know that the delta is 1 by, the delta is 1 divided by root of pi f mu sigma, pi f mu sigma. Okay, but this is anyway same thing as what we really want the same expression for alpha and beta. Okay, but I would like to say this is also equal to 1 by delta. Actually, we have delta is equal to 1 by alpha. Okay, so alpha is equal to 1 by delta. Okay. Okay. So next thing, we know that the gamma, the propagation constant, is given by alpha plus j beta. As we know, this alpha and beta are same. I can write this as 1 plus j, and I know that alpha, okay, is equal to 1 by delta. 1 by delta. So we can write this as 1 plus j by delta. Okay. This 1 plus j I can write it as 2 root of angle 45 divided by delta. Okay. So you could see that we are interested to write all these wave characteristic parameters in terms of a skin depth now. Okay. So alpha is equal to beta equal to 1 by delta, and the gamma, which is propagation constant, which is alpha plus j beta, which is a complex constant. With simple modification, that is alpha and beta are equal, which we can take common, and 1 plus j, I can write it like root 2 and angle 45. Okay. And alpha is 1 by delta, that is what we have here. Okay. So next, we know that the velocity of phase velocity propagation is given by omega by beta, which is omega by delta. Okay. And lambda is equal to 2 pi by beta, which is, we can write 2 pi delta. And we know that the intrinsic impedance of the medium is given by root of pi f mu by sigma into 1 plus j. 1 plus j. Okay. So I can simplify this further. Okay. I can simplify this further. That is root of pi f mu. I will multiply sigma over here and also sigma in the denominator. Okay. So already I have a sigma here, so this square, and further we have like 1 plus j. So you could check that this I could write it as pi of mu sigma into 1 plus j. Okay. But I know what is this root of pi of mu sigma, which is equal to delta times 1 plus j, that is skin depth times 1 plus j. Okay. Yeah. I'm sorry. This pi of root of pi of mu sigma is equal to 1 by delta. So this will be equal to by delta, and we have the root of the sigma square is equal to sigma. So we have the sigma here. So this is 1 by delta sigma. Okay, that's quite simple. So what we have done is I multiplied sigma and sigma. Okay, I multiplied the sigma in the numerator and also in the denominator. So so I have separated numerator and numerator and denominator. Okay, this factor we could observe that it is equal to 1 by delta. So that is here what we have written. Okay. And further, the root of sigma square will be the sigma. Okay, that is present over here, and 1 plus j is simply followed. Okay, so that is the simplification for that eta, and we can write the eta in one more way, that is 1 divided by delta sigma. 1 plus j is nothing but, as we say, root 2 an angle of 45. Okay. Yeah. So you could see that we try to write all those particular wave characteristic parameters of a good conductors in terms of the skin depth. Okay. And I feel that remembering, okay, remembering the formula of a skin depth, okay, it is delta is equal to 1 by root of pi of mu sigma, or 1 by delta equal to this. Okay, and remembering this gamma, velocity, eta, and all this intrinsic impedance in terms of skin depth is quite easy. Okay, it's quite easy as compared to what the wave characteristic parameter we have for the good conductor. Okay, so you could really check that the intrinsic impedance for that. The intrinsic impedance for a good conductor is 1 plus j by skin depth times sigma. Skin depth times sigma. What I mean to is, remembering this formula is quite easy as compared to remembering this one. Is that okay? Or you can remember this one. It is really the same. Okay? Yeah. Anyway, these two are quite simple to remember, okay? Or even you can really remember these one, okay? Yeah. So once we have really understand that is how to write this wave characteristic parameters in terms of the skin depth, and I emphasize that it is really worth of remembering the wave characteristic parameters for a good conductor in terms of the skin depth as compared to this original formula. Okay, so next with this I can also write my expression for an electric field in terms of the skin depth, which is given by Ex naught e to the power minus alpha z, okay, alpha z, and I know what is alpha is. Alpha is 1 by delta, so 1 by delta. Then cos of omega t minus beta z, but beta is 1 by delta. Okay, that is Ax hat. Similarly, the magnetic field is given by Ex naught divided by the magnitude of intrinsic impedance, which is given over here, which is delta sigma into e to the power minus z delta cos of omega t minus z by delta. You have, okay, even this comes into the picture. Okay. Yeah, I'm sorry, this is actually, it is root 2 divided by that will jump over here. So you have a root 2. So the one more comes is an angle of 45 degree, and this is a y hat. Okay, so this is the expression for an electric field and magnetic field in terms of the skin depth. Okay, in terms of the skin depth. So this is the whole story of wave propagation in the good conductor. Okay. So all what we have seen is, if I really try to summarize from a free space, in free space wave propagates in phase both E and H field without any loss. Okay, and with the speed of a light in a free space. Whereas in perfect dielectric, the wave propagates in phase but with a reduced speed. Okay, and the speed reduced by a factor of root of mu r epsilon r. Okay, what happens when it comes to conducting medium? When it comes to conducting medium, the wave propagates. Okay, first of all, they try to attenuate as they propagate, and E and H field are out of phase by a factor of theta eta. Okay, then we try to approximate. Okay, by using a by using the concept of a loss tangent. Okay, this conducting medium as a good conductor and good dielectric. Okay, as we said that in conducting medium, the wave really attenuates as it propagates through the medium. Okay, we define a concept of a skin depth. Okay, this skin depth is really applicable even for conducting medium also. It is a general medium. Okay, but we have really discussed with respect to good conductor, and that skin depth is given by 1 by alpha. 1 by alpha. That is the depth, okay, to which the wave can really propagate. Okay. Okay. And that really depends upon even on the frequency also. Okay. Yeah. So the next thing we said that, okay, by taking the wave characteristic of a general medium, okay, we try to approximate the formulas of all the wave characteristic of a general medium, okay, for a good dielectric. Okay. Similarly, we followed the same procedure for a good conductor. We took up the wave characteristic of a general medium, okay, and we try to approximate it by applying that loss tangent concept, okay, and we got an approximate values of wave characteristic for a good conductor, and that is what we have. And we studied the concept of a skin depth, okay, which measures the depth to which the wave can propagate in a given medium, okay, and that really depends upon the frequency. And next, we load the whole characteristic of the wave characteristic in terms of a skin depth. Okay. So we are left now with the last topic of this module 5 and of this course, that is Poynting's theorem and the wave power. Poynting's theorem and wave power. Okay. Now what pointing theorem states that the pointing theorem states that the net power flowing out of a given out, okay, power out of a given volume V, volume V is equal to time rate of decrease, the time rate of and rate of decrease in energy stored within V, okay, minus ohmic loss, okay. The pointing theorem and the wave power, okay. The statement says that, okay, the net power flowing out of a given volume is equal to the time rate of decrease in the energy stored within a volume V minus the ohmic loss. Okay. Now the pointing theorem, okay, will tell you about the direction of propagation, the direction of the flow of an energy. Okay. Pointing theorem will also help us to find the direction of propagation, the direction of and flow of an energy. Okay. It also tries to give the power flowing out of a volume, okay, or a power density. Okay. Now what this theorem tells is quite simple. Okay. There is power flowing in some certain region, okay, having a volume V. Okay. Now this power, okay, is being delivered, okay, or you could say that is being consumed, or there is some ohmic loss. Okay. Now what will be a power which is flowing out of this volume? It will be obviously okay, will be obviously equal to this, okay. That is the power which is consumed, okay, and minus this particular ohmic loss. The remaining power will be available at the from this particular volume. Okay. And that is what is being stated in this particular statement. Okay. So you have some power flowing in a volume. Okay. There is some power is stored in electric and magnetic field, and there is some ohmic loss. The remaining power, okay, is available from this side, flowing out of this volume. Okay. So let us try to derive this particular pointing theorem. Okay. And if you want anything, okay, in electromagnetic wave, we have to begin from the Maxwell's equation. So we know that we have Maxwell's equation, del cross E is equal to del cross E equal to minus dou V by dou T. In terms of H field, I can write it as minus mu times del dou H by dou T. And similarly, del cross H is equal to sigma times E plus, okay, epsilon times dou E by dou T. Dou E by dou T. Okay. So let me call this as equation number 1, and let me call this as equation number 2. Okay. So let us try to make a dot product. Okay. Dot product both sides. Dot product both side of equation 1 with H with the so first we'll take a dot product both the side of equation 2 with the E. So which means that it is del dot, I'm sorry, it is E dot del cross H is equal to sigma times E dot E, which is E square. Then it is E dot epsilon times dou E by dou T. Okay, so let me call this as equation number 3. Okay, so next I say that we have an vector identity. We have a vector identity that is del dot del cross A is equal to B dot del cross A minus A dot del cross B. So in our case, let us consider, in our case, that A is equal to H and B is equal to E. By doing, by making this substitution, that is considering A as H and B as E field, you can write this as del dot del cross H is equal to E dot del cross H minus H dot del cross E. Okay. So let me check what we sorry. So actually we have a vector identity. Actually it is A cross B. Okay. Yeah. So we have a vector identity saying that del dot A cross B is equal to B dot del cross A minus A dot del cross B. Okay. And here it will be actually like H cross E. Okay. So now you could check that in this particular equation number 3, I am interested with E dot del cross H. And you could check that is here, E dot del cross H. So let us solve for that. What we get is E dot del cross H is equal to del dot H cross E plus H dot del cross E. Just I'm solving from this one. So let us plug in that. So let us plug in this E dot del cross H in the equation 3. So what we get is del dot H cross E, okay, plus H dot del cross E, okay, is equal to sigma times E square plus E dot epsilon times dou E by dou T. Okay. This is quite a simple thing. Okay. There is one more fact, okay, I would like to simplify. That is E dot epsilon times dou E by dou T. Okay. So first thing, when you make a dot product, okay, it reduces to a scalar. Okay. So you take some T field which has say all components x, y, z. You make a different shape. You'll get back some field having again back all the components because it's a differentiation with respect to the time. So when you make a dot product, okay, it reduces to a scalar. So I can write this as like E times dou E by dou T. Okay. And further you could check that I can write this as 1 by 2 epsilon times dou E square by dou T. Okay. Now, why this is so? Because it's quite simple that I mean we can try to convince this by making like a back propagation. Okay, I will start from here and I'll come back over here. So you have some e function, I mean e is a function of both space and time. So when you differentiate, you will write it like a 2e, okay, 2e, and again you need to differentiate this back with respect to time. So dou e by dou t, dou e by dou t, okay. So the 2 and 2 get cancelled. So you could check that you get back again the same thing. So which means that this thing I can write it like this. Okay. Yeah. So with that, one more simplification, I could really write this as del dot h cross e is equal to h dot del cross e is equal to sigma e square plus 1 by 2 epsilon times dou e square by dou t by dou t. Okay. So we have now this expression with us. Okay. Yeah. Yeah. So now let us try to do one more thing, that is taking a dot product, okay, of the equation 1 now, okay, equation 1 with h, and the equation 1 was, I would like to write here, the equation 1 was del cross E equal to minus mu dou h by dou t. This was our equation 1. If I take a dot product with respect to the h both the side, so it is h dot del cross E equal to minus mu h dot dou h by dou t. Okay, and we know that as I discussed over here, this can be written as mu 1 by 2, mu 1 by 2, mu 1 by 2, dou h square by dou t by dou t. Okay, so we could really check that. Now we can plug in this particular thing what we have here. Okay. That is, I can replace h dot del cross E with this one as what I have obtained just now. Then you could say that you're almost done with this pointing vector h cross E. Okay. Sorry, this is actually plus over here. Yeah. So plus, which is with this substitution, it is like a minus mu 1 by 2 dou h square by dou t, okay, which is equal to the what we have here, that is sigma e square plus 1 by 2 epsilon dou e square by dou t. Okay. Yeah. Okay. So we are almost done. You could check that I can write this h cross E as E cross h, so it will be minus. So minus del dot E cross h. Okay. And I'll take this term over this side. So which is mu 1 by 2 dou h square by dou t plus sigma E square plus 1 by 2 epsilon dou E square by dou t. Okay. Taking this minus this side, I can write the whole thing as, okay, del dot E cross h, okay, is equal to minus mu 1 by 2 dou square dt minus sigma times E square minus 1 by 2 epsilon dou E square by dou t. This is Poynting's theorem in the point form. This is a Poynting's theorem in the point form or differential form. Okay. Yeah. So we say that this is point form of Poynting's theorem of Poynting's theorem. Okay. Yeah. Now, if you want really a power coming out of a volume, we need to do this volume integral throughout the thing. This is giving, okay, giving Poynting's theorem in the point form. Okay. So now let us make this volume integral of this expression. So what we get is volume integral of del dot E cross H dv, which is equal to volume integral. I try to club these two terms, okay, which is minus of mu 1 by 2 dou h square by dou t, okay, minus mu 1 by 2 dou h square by dou t. Then I take this whole minus outside, okay, plus integral of epsilon by 2 dou e square by dou t, okay, that's here, and this one more term minus sigma e square, okay. So this is we need one more thing, okay. So let us apply divergence theorem. Apply divergence theorem, okay, to this particular term, left hand side, which converts the volume integral to the surface integral. So we can write this as surface integral of E cross H dot ds. Okay, the volume integral converts to a surface integral, and that's what we are done. This is minus of mu of 1 by 2 dou h square by dou t plus volume integral of epsilon by 2 dou e square by dou t minus sigma e square. Okay. That is what we got. The Poynting's theorem, which we have made a statement, we got its corresponding equation. Now, what this term is trying to tell, this is total power leaving a volume. Total power leaving volume. And this one is rate of decrease in energy stored this rate of decrease of energy stored in E and H field, that is combining this whole thing, E and H field, and this is a loss, that is ohmic power loss. That is the ohmic power loss. Okay. Okay. This is the Poynting's theorem is. Okay. So as I said that, okay, there is a power flowing in a volume. Okay, and there is an interaction of this this electromagnetic waves, okay, with the charge and the currents, okay, okay, or we could say that there is, okay, loss due to an ohmic loss, okay, and there is power absorbed, okay. Now, what is power will be flowing out, okay? Power flowing out will be this power which is flowing in minus all these things, okay. Whatever is remaining, you are available here as a power flow outside the volume, okay. And that is what is given to me as total power leaving a volume as this one, which is given by E cross H dot ds surface integral. Okay. Now it is E cross H dot ds, which really it means that this should be a power density. This should be a power density. Okay. And this is, as I told that, okay, this represents stored electric energy in, in electric field, okay, stored electric energy, stored magnetic energy. That is what we have is, okay. So we are speaking in terms of power, and power is rate of flow of energy, okay. So you could, and that's what we have is, it's a rate of decrease of energy stored in E and H field, E and H field, okay. Yeah. So you could really recall from the static field, okay, the energy stored in what we could say that in an electric field which was given 1 by 2 d dot E, or we can write it as 1 by 2 E square. And whereas energy stored in magnetic field was given like B dot H, or which we could write it like, and this is epsilon times E, this is mu times H square. These are energies 1 by 2 E square. Okay. And now I'm speaking of power, so it is rate of. So rate of. Okay. It's exactly 1 by 2 mu. Okay. Dou H square by dou T, which tell you about the rate of, because of this minus sign. Okay. It indicates a rate of decrease of energy stored in E and H field. Okay. It's a combined. That is, we are subtracting from this power in, okay, from this stored energy and the ohmic loss. The remaining thing is available to us. Okay. Remaining thing is available to us. And the ohmic loss. And we know that in Ohm's law, according to this, it is given by the J equal to sigma times E is according to an Ohm's law over there. Okay. Yeah. So now we could really check that. Okay. Some interesting factor is what we really want to recall is, okay. So this particular expression which we have derived for a static field, that is energy densities 1 by 2 d dot h and 1 by 2 epsilon 1 by 2 d dot e for an electrostatic field. They are really still valid for our time varying cases also. Okay, time varying cases also. Okay. So with this Poynting's theorem, okay, what we would like to say is that, okay, there is interesting factor about this vector product, okay, the vector product, which is denoted by as S, and it is, the vector product is E cross H, okay, and this is called as Poynting vector. This is called as Poynting vector, okay, and you could really check that it has an unit of watt per meter square. Watt per meter square. Now this S, okay, represents, okay, represents instantaneous power density instantaneous power density vector associated with E and feed associated with E and feed at a point at a point. Okay. So S, which is given by a vector cross product, it is E cross H. It is given a name as pointing vector, and it is measured, and it has a unit of watt per meter square. It is power density. Okay, yeah, power density. Okay, and we say that S represents. Okay, this is also important. It represents instantaneous power density. Okay, instantaneous power density vector. Okay, associated with an EM field at a given point. At a given point. So obviously, if you know what is the power density in a given region, okay, if you want to find a total power leaving some volume, we need to integrate. That is S dot ds. S dot ds, as it is a watt per meter square. Okay. So which is measured between the watt. Okay. So once understanding about this pointing vector, pointing theorem, okay. So there is some note, okay. There is note. If you know the unit vector, if you know what is the unit vector along the direction of an electric field, and you know what is unit vector along the direction of an H field, okay, we say that if you make a cross product of AE cross AH, you get the direction of propagation, and AK represents the direction of propagation. Okay, and that we have really understood it from the pointing vector, pointing theorem, because we come to know that, okay, from pointing vector, that is, which is given by E cross H, okay. So there was a flow of power in the direction of an E cross H, which means that the wave is propagating along the direction of E cross H, and hence we can use this to identify the direction of propagation. So the other things are also useful, like if you know what is the direction of propagation and if you know what's the direction of an electric field, okay, you can find direction of the magnetic field. So these things are useful. That is AH hat and AK hat cross AH hat is equal to AE hat. Okay. So we have seen about the power density. Okay. So, but the practical measurable quantity, is the time average power. The time average power. Okay. So we would like to define time average pointing vector. That is denoted within a bracket SZ. Okay. That is integration of S, which is a function of both space and time. Okay. And average over a one-time period. Okay. So this is defined as time average power density. density. Okay. So this particular thing, okay, we have an equivalent expression in phasor form. Equivalent expression in phasor form. This is working in time domain. We can really work it easy in the phasor domain, which is given as 1 by 2 real part of ES cross HS conjugative. Okay. This is also a time average power density in the phasor form. Okay. So that's all for today. For this session, we'll stop here.